Read the timer. That's然后自动按那个的什么？
Yeah, there was. I don't think my meetings are real quick. There was one coach, and there was that part of it. Well, they didn't. It was actually really easier to do went to palindrome. This is really very hard, right? Palindrome is you're checking to see if the word is palindrome. But so you have unlimited. It has two flags. I'm not sure what two parameters beside the word. One is ignore case. So we can work there. So like this would be a palindrome. There's a way to approach the board with the board goes down to the palindrome. Space. The other just would be a palindrome. So yeah.
Okay, let's get started. So, first of all, just a reminder, the product lab 1 will be due today at 5 p.m. I did give you guys a 2-day extension. And this page, you can check your submission status. We wrote a script that every 10 minutes we will grab your code. I'll check your commit status from your project 1 branch of your GitHub or Bitbucket repository. Right? So if you don't see your team showing a commit tag and commit timestamp there, that means we don't have a submission from you yet. And we will stop, this script will stop about 10 minutes after 5. Which means if you commit anything 10 minutes after 5, we will not be using those for our grading purposes. Any question regarding this? You see your team number up here. Example team 10, team 19, 20, 24, 26. If you are one of these teams, make sure you follow the submission instruction and commit your code before 5 p.m. Okay? So, we're going to continue our discussion on hashing. So, quick review of what I said last time. you're gonna have a set of data entries. We specifically want to use alternative 2, right? Alternative 2 of data entry is record ID plus a search key value k. Okay? And if you're going to use alternative 2 to represent your data entries, then naturally you're gonna have one data entry per record. One data entry per record. So if you have n records, you end up with n data entries. However, the number of data entries you can fit in a page is going to be much larger than the number of records you can fit in a page. In other words, n over b prime will be much larger than n over b. Right? Where b prime is the number of data entries you can fit in a page, and b is the number of records you can fit into a page. The reason for that is the size of data entry is much smaller compared to the size of record. Okay? So that's what we said last time. And if you have a git hash function that does a balanced distribution of your data entry into this n buckets, then what you have is essentially if you try to look up a particular value, you only need to pay 2 IOs to retrieve that record. The reason is you pay 1 IO to go to the bucket page containing the data entry with that search key value k. Then once you find that data entry, you use another IO to retrieve the actual record, following the RID value of that data entry. But there's a strong condition here, which is you must have a balanced distribution of entries into these buckets. Okay? And each of this is a page that contains multiple data entries. How many you can fit in a page? Well, that's the value of d prime. That's what we said, right? Which is using page size divided by data entry size. Okay? You can get the floor of this, that gives you d prime. Okay? And when you do not have a balanced distribution, what that means is some buckets will receive more data entries than some others. Then a single page may not be able to hold all data entries going to that page. Okay, so suppose you have more than b prime number of data entries being hashed into a particular bucket, what happens? Well, you will end up with what we call overflow pages of that bucket, because you do need to allocate more pages in order to accommodate those entries that are more than b prime that are coming into that particular bucket. Does that make sense? And in the extremely worst case, if you have a long chain of overflow pages, that defeats the purpose of using hashing index. In the worst case, you may have a single bucket with this many pages. Right? All your data entries are being hashed into that single bucket. The number of overflow pages in that single bucket is n over b prime. I mean, it still serves a purpose, right? As I argued last time. Even in that case, if you do a linear scan over your data entries to find the search key value k you are searching for, then follow the RIDs to retrieve the record, you may still be better off than this, than n over b. Right? Simply because, oh sorry, someone made a mistake here. Just yellow bit. Okay. So you may be still better off by doing the scan on these overflow pages, but still this is fairly expensive, right? So that's the idea of static hashing. So key question boils down to how do you define a good hash function h such that for different key values, search key values, you can obtain a somewhat balanced distribution of these data entries into different buckets. Right? So that's essentially the question we need to address. And for now, just remember we're going to use this particular hash function. I will explain later on why this is a good hash function. What we're going to do is use hx equal to ax plus b mod p, then mod n. Okay, so there are a couple of things here to note. P here is a big prime number. Okay, a big prime number. randomly chosen, and A and B are randomly chosen from the field of P. So the field of P is a mathematical definition, and it refers to 0 to P minus 1. And to be precise, let's get rid of 0, because sometimes 0 can be tricky to deal with. The field of P is from 1 to P minus 1. So you randomly choose two numbers, A and B. A and B do not have to be prime. From the field of P, P the prime. Then you simply do AX plus B mod P. The whole thing mod n. The reason is to make sure the output is in the range of 0 to n minus 1. I agree there's a little bit of abuse of notation. This n is different from this n. This n denotes the total number of records. Here, where this denotes the number of buckets you have. Okay? Alright? So how will we follow this? Now, this actually is a fairly good hash function, which I will argue for you later on. So now just take this as a really good hash function that will typically give you a fairly balanced distribution no matter what are the set of value x. What are the sets of values x? Yeah.
How do we calculate A and B?
How do you calculate? Well, you just randomly choose two numbers.
Like, I mean, how do you know which ones are in the field?
Well, the field of B is from 1 to P.
Oh, okay. I was thinking of something different.
Okay, no worries. So the field of P is from 1 to P minus 1, integers. All integers from 1 to P minus 1, you randomly choose two numbers out of them, and fix that as your A and B. And that's your hash function. Okay? So one problem with static hashing is that even given a good hash function, somebody, an adversary may come in and say, I can look at your hash function design and keep pushing particular type of values x such that they all are hashed to the same bucket, so that you can develop this long overflow chains in those cases, right? So how do you address that? Well, we address that using dynamic hashing. There are two particular dynamic hashing techniques we're going to talk about. One is called extendable hashing, and the other is called linear hashing. So, extendable hashing, the idea is as follows. The main idea behind the design of extendable hashing is to say, I do not allow overflow buckets to exist at all. So there are no overflow buckets. So things like this is not allowed in extendable hashing. How do you make sure that though? What happens if you do have overflow buckets? What do you do? Well, the idea is I will double the number of buckets I have whenever an overflow has occurred. I'm going to double the number of buckets I have. Okay? Whenever an overflow has occurred anywhere, and redistribute entries from the overflow bucket into the existing bucket and the newly created bucket. Because I have doubled the number of buckets I have, I can do that. Make sense? You can think about this as you have a few drawers, you put stuff into those drawers. Whenever a drawer is overflow, meaning too many stuff, you cannot close the drawer anymore. Suppose there are 4 drawers at the moment, and one of the drawers, drawer number 1, is overflowed. You try to put something over there, but it doesn't fit. Know that this something cannot go to drawer number 2, 3, or 4 because it has to follow your hash function. It's being hashed to drawer number 1, so it has to go there. Even if you have space in drawer 2, 3, 4. Does that make sense? And whenever this happens, the way you're going to address this is I'm going to add 4 more drawers. 5, 6, 7, 8. Okay? I'm going to redistribute everything from that drawer number 1 into drawer 1 and drawer 5. And everything else stay intact. That's essentially the idea. And why 1 and 5? You may wonder. Why not 1 and 6? Why not 1 and 7? Why not 1 and 8? That has to go with binary numbers, binary encodings. So why binary number? Why binary encoding? Why that has to do with what we are talking about here? Okay. All right. Let's look at binary numbers. Binary number with one bit, which is only one bit. Round one. Binary number with two bits. What happens? What do you have? What about binary? This is with two bits, right? What about binary number with three bits? Okay, I'll leave it here. Huh? So, do you observe some pattern here? Now, drawer number 1, or if I change my index, instead of using 1, 2, 3, 4, I use 0, 1, 2, 3. Okay? Shift everything down by value 1. Like typical index value in your array. Huh? So that's drawer 0, 1, drawer number 0, drawer 1, drawer 2, drawer 3. So what's the special thing about drawer 0, which is here, and the drawer number 4? The drawer number 5 now becomes drawer number 4, right? I decrement the index value by 1, which is what's so special about these two values?
I was just going to say that the two right numbers are the same.
Yeah, if you look at them, the lower two bits of them are identical. You cannot distinguish them. In fact, this becomes, when you're using 3 bits to represent 0, this becomes this value, right? The lower two bits are identical. You can only distinguish them at the highest bit, at the most significant bit. Make sense? This actually gives you a way to redistribute item in that drawer number 1. Initially, you decide, okay, all items with lower 2 bits equal to 0, 0 goes to drawer number 1. All items with lower 2 bits equal to 0, 1 goes to drawer 1, drawer 0. And all items with lower 2 bits equal to 1, 0 goes to drawer number 2. And lastly, all items with lower 2 bits 1, 1 goes to drawer number 3. That actually covers all the possible cases, because I don't care what is the value associated with that particular item. I can always just look at those 2 bits, and there are only 4 cases to consider. I partition them into 4 drawers. Done. But if you have too many items with lower 2 bits equal to 0, 0, you have a problem, because drawer 1 reached the maximum capacity. Does that make sense? So what you do, you introduce 4 more drawers, which is these guys, or buckets. You're talking about this in the content hashing. And you see everything goes here, there are a bunch of stuff goes here. Some of them will stay here, some of them will go here. The reason they were here to begin with is because the lower 2 bits of those guys are all 0, 0. I'm only looking at the lower 2 bits. But I can no longer distinguish them enough by looking at just 2 bits. Now I look at what? The lower 3 bits. Some of them will stay here, some of them will go here. And by that, hopefully that will address my overflow problems. That's the intuition behind this design. Does that make sense? Yeah.
When you do that, do you also take care of the other ones that are hashing?
Very good question. Do you also redistribute those guys? I mean, those items that were here, meaning the lower 2 bits are 0, 1, you could, technically you could redistribute them into this and this by looking at the lower 3 bits. But you don't have to, because you don't have an overflow problem in that drawer number 1. Meaning that drawer number 1 hasn't reached the maximum capacity yet. Of course, you can do this as a precautious measure, like redistribute them into the other drawers too. You can do that as well, but you don't have to. Does that make sense?
Yeah.
So that's the intuition behind this example. If you wonder what happens if this or any of this become overflow again, well, use the same idea, double the number of drawers you have, but at this point, doubling is no longer just going to introduce 4 new drawers, it's going to introduce what? 8 new drawers. Fundamentally, the reason is by adding 1 more bit, you're looking at, even add just 1 more bit, that always double the range of your index values. Okay? Alright, so that's kind of the idea. So more specifically, what I'm going to show you on the next few slides is really just to capture what I have just said. Okay? And here, what I'm going to do is, I'm going to suppose I have a record R. Let me introduce this first. Then talk about the example in the case above. So I have something called directory. This directory is somewhat like what I have here. To remember how many bits I'm currently looking at, and by looking at this many bits, how many drawers or buckets I have. So that directory is actually the same as what I have done here. So for example, I'm looking at the lower 2 bits at the moment, and the drawers are from 0 to 3, 0, 1 to 3, in binary format. Essentially, that's what the directory is for. Okay? As you can tell, directory is fairly small. You can fit this easily in a page. This is fairly small information you fit into the page. And each of these buckets is a page, is a disk page. And they contain those data entries. Does that make sense? Those data entries. So, for example, what's here is those records with. So here, to make the presentation easier and clear to understand, I'm no longer using the hash key value k. I'm using the hash version of those hash key value k. So what I show in the slide is not the value k itself. I'm not showing the value k itself. I'm showing the hash value of that. So the data entry k RID becomes essentially hash value of that or RID. That's what I'm showing in the slides. So what this means is there's a hash value k after applying the hash function becomes the value 4. There's another hash value k after applying the hash function h becomes value 12, so on and so forth. Okay? This is really done for the ease of illustration. In practice, in system, you don't store the hash value. You store the original hash value, original search key value k, because you need that search value k later to do the search. Okay? Question on this? Pretty good on this. Now, what's so special about these hash values? What's special about these hash values? Go ahead. Huh? Multiple of 4, yeah. And? Anything else? I can also see there are multiple of 2. Right? What's so special about these hash values? One observation that's clear, if you are multiple of 2, what will be the last bit in binary representation? Must be 0. If you are multiple of 4, as you said, what's so special about that? Well, the last 2 bits must be 0. That's exactly what happened here. The last 2 bits of these hash values are all 0. That's why they end up being Barkey number 1. Okay? What about this guy? This value 10. Why 10 is 0? Because the last 2 bits of 10 is what? Is 1, 0. Okay? 8 is 1, 0, 0, 0. Right? This is value 8. So 9 is
two bits of 10 is 1, 0. Okay, finally, what about these guys? Well, the last one bit of them is 1. And this shows a special case. For this particular bucket, I'm not using the last two bits to distinguish them. Because if I do, they actually do not belong to the same bucket. They have different last two bits. But looking at just last one bit, they are the same. The last one bit of all these guys, the last one bit of all these guys is the value of 1. That's the significance of this value here. This is what we call local depths. This is what we call global depths. Global depths tells you how many bits you are looking at, how many lower level bits you are looking at in order to index different buckets. Local depths, the value of local depths tell you how many lower level bits I'm looking at to distinguish elements within this bucket. Obviously, there's a constraint where your local depth must be less than or equal to global depths. Does that make sense? No matter what if, why not we remove this and introduce another bucket called 1, 1, and this bucket become, this bucket just 0, 1, and use global depth 2 or local depth 2 on both of those buckets. You certainly can do that, but if you do that, you are wasting your space. You don't have to do that. The point is, when you go from here to here, when you double the number of buckets you have, or the number of drawers you have, if you think about it, you only need to redistribute items. This goes back to Jared's question, actually. You only need to redistribute items from that overflow bucket. For those other drawers or buckets, they are fine. You don't have to do anything to them. Even though you have doubled the number of directory entries, you don't necessarily need to double the number of bucket pages you have. That's what's going on here. Question?
It seems like if you don't redistribute from second, fourth, and fourth, then later when you want to find out which bucket is some record is that you will not be able to find out.
That's a very good question. So the question is, if you don't redistribute that, if I do a search over this, how do I know which bucket it actually locates at? Sometimes, if I do a search over here, do I know it's here or in another bucket? I will talk about that later on. Let's talk about the structure of this first, then we come back and look at how the searching is done. Okay? Now, let me give you some. If you look at the value of 5 and 7, so suppose I have two different records with search key value hashed to 5 and 7. 5 in binary is 101, 7 is 111. If you look at the lower two bits, they are actually different, but if you look at just the last one bit, they are the same. Okay? Now, suppose this is what I start with. I want you to insert value 21. Again, these values, when I say values, to ease the discussion, they are no longer just the search key value. It's the hash of the search key values. So some search key value k is hashed to value 21. Another search key value k is hashed to value 19, and so on and so forth. Does that make sense? That's the assumption of our discussion. Now, these hash values 21, 19, and 15 has these binary representations. And if I insert 21 into this, can someone tell me where 21 should go? Huh? Bucket B. Bucket B. Bucket 01. The last two bits is 01, so 21 should go here. And what happens? You don't have space for it. So this results in an overflow bucket. Make sense? Whenever you have overflow, remember what I said earlier, what happens? You double the number of buckets you have, or double the number of directories you have. which in other words, you increase the local depth from 2, the global depth from 2 to 3. And you increase the local depth to, you increase the local depth from 1 to 2 to distinguish them. And 7 goes to here, 21 goes there, and you are done. You update the pointer. Why is this? Let me repeat this process again. In the general case, you would double the number of buckets you have. But this is one of the cases where you just doubled the number of buckets and you didn't redistribute items for some of the drawers. And one of those became overflow, but you do have additional space for it before you need to do the doubling operation again. And that's what's going on here. The local depth is still less than the global depth in this particular case. So you don't have to increase the global depth yet. All you need to do is to increase the local depth so that you introduce a new bucket and redistribute everything here by looking at last 2 bits now, instead of looking at just last 1 bit. Do all of you follow me on this? And if you do that, the last 2 bits of 1 is what? Is 0, 1, obviously. What's the last 2 bits of 5? 5 is 0, 1 as well, right? 0, 1, 2, 3, 4, 5. 5 is, last 2 is 0, 1 as well. Last 2 bits of 7 is what? We did the calculation, is 1, 1. Right? Last 2 bits of 7 is 1, 1. So 7 won't stay in that bucket anymore. It has to go to this new bucket. And 13, if you do the calculation, the last 2 bits is also 0, 1. So it stays. And 21, the new entry, the last 2 bits is 0, 1, so it stays in that bucket. Then finally, I update this pointer for the global direction 1, 1, no longer pointing to that existing bucket, I point to this new bucket with last 2 bits equal to 1, 1. Okay, so that's what happened. Do all of you follow this update procedure? You're happy for now, right? Your drawers are okay, every item goes to the right place. Fantastic. Now you have a problem though. I'm going to keep inserting into this bucket. So for 19, the last 2 bits 1, 1, you know exactly where it should go. 15, so far so good. Okay? So I move this picture to here. So that's where we are right now. That's the state we are in right now. Now I'm going to insert 20. Where 20 goes? Can someone tell me?
No, before part. So we could have one bucket for 0, 0 and 1, 0 as well, right?
Say again. For the previous example, for this one, yeah.
Yeah. This initial stage we have 3 buckets, A, B, C.
No, initially, yes. In this case, we have 3 buckets. That's right.
Instead, we can have only 2 buckets for 0, 0 and 1, 0. Like, you can combine 0, 0 and 1, 0 as well, right?
Well, you cannot, because if you do that, this will be an overflow.
Oh.
External hashing, the whole idea is no overflow buckets at all.
If the bucket is empty, then we can combine.
Yeah, of course. If you delete 10,
then we can remove.
you can deallocate this bucket, make this pointer point to here, and when that happens, you decrement your global depth by 1, because you no longer need 2 bits to distinguish them. You only need 1 bit to distinguish everybody. At that point, you decrement your global depth by 1. Does that make sense? Okay, so where 20 goes? We need to figure out the binary value of 20, right? 20 again is some hash function k, some cert key value k is hashed to the value of 20. So we're now trying to insert this particular data entry with cert key value k and a computer RID, such that this is true. We're trying to insert this data entry, right? 20, the hash value of 20, 16 is 10000, right? And 17, 18, 19, so 20 is 100. Right? So 20 goes to the first bucket. What happened now? Now you have overflow. Not only you have overflow on this bucket, the local depth is already at the maximum, equal to the global depth. So the trick of increasing the local depth no longer works. At this point, you have to what? You have to double the number of buckets you have, double the entry you have, which means increase the global depth by 1. Okay? You increase first the local depth by 1, meaning you are looking at the last 3 bits to distinguish this item and this new item 20. If you look at the last 3 bits, only 32 and 16, as last 3 bits equal to, I just said, 16 is 1000. So the last 3 bits is 0. So 16 stays. 32 also, right? But 4 and 12 have to go away. Because the last 3 bits of them are no longer 0. So 4, 12, and 20 goes to a new bucket. And you increase the global depths. And what we're doing here is essentially what my answer to Jared's question earlier, that we do not redistribute items from other drawers. We keep them the place they are. The reason for us to do that is that saves us, at least for now, the trouble of creating those new drawers. Virtually, I create the index value to cater for them in my directory entry, but I do not physically create those buckets or those drawers. I only create one new physical drawer, one new physical bucket to accommodate that overflow bucket. For those other ones, I only create a space holder for them, but I do not physically allocate a new drawer yet. That's essentially what's going on. Any question on this purpose? And these 3 guys are allocated to this new bucket. That's because the last 3 bits of them is 100. And you can also, a final thing I want to say before I take your question is, you can easily prove this. Once you are given an overflow bucket, you can always, by looking at one more bit, they are partitioned into 2 groups only. Why is that? Can someone give me a proof of that? Why, when I have these guys, why I'm guaranteed to have only 2 groups, 32 and 16, one group, and 4, 12, and 20 in another group? Why is that? Why not 3 groups? Why not 4 groups? Why not 10 groups? Huh? The proof is actually very simple, because we are indexing them by binary representation. By looking at one more bit, it's either 0 or 1, right? What else? Only 2 groups. Right? No matter what the existing index are, it could be whatever. I look at one more bit, it's this or that. There are only 2 possible scenarios. And I'll prove. You had a question, go ahead.
How do you determine local depth?
How to determine local depth? That's illustrated by this example here. When you have increased the global depth, and you didn't allocate a new bucket after that, then the local depth stay intact. For these guys, the local depth stay intact. But when you have doubled the number of direction entry you have, meaning increasing when you have increased the global depth, at the same time you have split that bucket and allocate a new bucket, then you have to increase the local depth as well, and local depth will be the same as global depth. That's how you determine the value of local depth. Okay? Now going back to your earlier question, how do we do search? Our search is actually fairly straightforward. Given any, if you try to search a particular value 5, certain key value k. Let's say I want to find this. Where is this data? What do? You apply a hash function k. You get the binary representation of this, and you look at the last global depth bits of this value to find the directory that's corresponding to this particular hash value. Then you follow the pointers. If it's hashed to here, you go here. If it's hashed to here, you go here. Okay? But if it's hashed to here, you go here. So in essence, if you are hashed to this or this, you end up in the same bucket. That's because the local depth of the bucket is behind the global depth. Let me throw out more questions, right? Is the following statement true or false? Okay? My following statement is local depth is only going to be smaller than global depth by 1. True or false?
False.
False. Why? Can you give me an argument for that?
We can have 4 more arrows when we double it.
When we double this again, if we keep, like for example, if there's an overflow here, I insert another 20, I keep inserting 20. So this will be overflow, right? Which causes the global depth to be incremented by 1, and number of direction entry doubled, yet out of this stay intact. The local depth still 2. And then the global depth is already 4. So you see how this goes, right? A worst case scenario for extendable hashing is 1. Someone tell me. What's the worst case scenario for extendable hashing?
Only one bucket keep on.
Only one bucket keep get overflowed, causing the global depth to be incremented by 1 all the time, meaning the number of directory entries to be doubled all the time. While most of the buckets still have a local depth of, in the extreme case, just 1, value 1. When your global depth might have already been, I don't know, hundreds or 200, which is huge if you think about it. Hundreds means that you have 2 to the power 100 directory entries. By that point, there's no point of using extendable hashing anymore because your directory entries become the overhead.
Does that then mean that your hash function is bad?
Yes, that could be an indication that your hash function is bad. Excellent. So designing a good hash function is critical. And we will be talking about that in a minute. How to design a good hash function. Before we do that though, I need to introduce yet another hashing structure. So that's extendable hashing.
So when we search for a number, so we are searching by global depth, right?
When you are searching for a value, you first apply a hash function over that value, and you get a binary representation of the hashed value, and look at the lower bits. How many lower number of bits you look at? You look at the global depth number of lower level bits to determine which bucket hold this value you are searching for.
So what if it is in a bucket that is
Can you speak a little bit louder?
So what if it is in a bucket that is less than the global depth?
That's fine. For example, if the lower 3 bits is here, this pointer will lead you to the red bucket. Once you're in a bucket, you just linear scan to find the value you are searching. That make sense? Okay, so that's extendable hashing. There are points to note. You can kind of read through this yourself after the lecture. Deletion, I'm not going to go into the details of deletion, but deletion, we talked about that, right? In the earlier, and one of you asked a question. I think you asked a question. I show you how to do deletion. Essentially, when every single bucket has a local depth smaller than the global depth, every single bucket has a local depth smaller than global depth, you can reduce the global depth by 1. That make sense? And get rid of a lot of pointers. That's when you can do the shrink operation. Okay. Next, we're gonna introduce the famous linear hashing. So by the way, hashing is a fundamental technique, right? If you guys later on go, in fact, if I were to interview for Google or Microsoft or whatever, right? The very first question I will ask is hashing. If you don't understand hashing, I don't think you belong to any of these companies. Seriously, I'm not kidding. I'm not joking. If you don't understand linear hashing, extendable hashing, you shouldn't be there. Because these are such fundamental things to understand, and they're simple yet somewhat really tricky, actually. Especially if you want to design good hash function. Now that's extendable hashing. Next, we're going to talk about linear hashing. So extendable hashing is super nice. However, it has this really nice property where it has no overflow buckets at any given time. But if you think about it, because of that, this can be a bad news for you. Can be bad news for you as well, because what if I keep overflow? I just keep introducing overflow to a single bucket. In that case, you end up with a really large, directory entries, but not very many data buckets. Does that make sense? And that's fundamentally because the way you construct extendable hashing, right? Whenever there's the overflow, you break that bucket, which sounds fine, but at the same time, I can make an argument that this is too aggressive a strategy, right? It's too aggressive. To give you an example, it's kind of like, what's a good example to use? So, a good example is, you keep placing, let's go back to that drawers example I gave in the earlier discussion. Right? A good example is, I have 4 drawers to begin with, and I keep inserting item to a single drawer. I don't use any other drawers. I just keep inserting to that single drawer. And whenever that drawer is overflowed, reach the maximum capacity, you introduce another drawer, and you don't introduce 4 new drawers. By now, you should understand that. We introduce only one new drawer, but we introduce the placeholders for 4 new drawers whenever that happens. Does that make sense? Initially, this is fine, but eventually, the placeholders you introduce over time, the overhead is too big. If I just keep introducing overflow to that single drawer, one single drawer all the time. So that's essentially what's going on. The fundamental problem, you're being too aggressive. Another alternative strategy is, what if, okay, drawer number 1 has a problem. Okay, I enter that into a queue. And I serve this in turn. I don't deal with that problem right away, but eventually I will come around and deal with that problem. It's kind of like you receive a 911 call at the police headquarters. If it's a shooting or whatever is a crime, ongoing crime, yes, of course, send your policeman over there right away. But if it's somebody like, oh, my cat is running loose and I need some help to find the cat or whatever, right? I mean, it's important, yes, it's important, but it's important to a degree that you need to send the police to that particular spot right away. Not necessarily the case, right? Not necessarily the case. If you have other kind of crime going on, that's much more significant than this. So what would you do if you're a police chief? If you're managing this police station, what would you do is you enter that into a queue. Somebody report this particular incident, and they queue up, and you deal with the problem in a round-robin fashion. Does that make sense? So that's essentially another strategy. Okay, drawer number 1 introduce a problem, let it be, and I will deal with whatever problem I have in turn, and eventually I will come to deal with that problem. In other words, I allow overflow bucket to exist for a short period of time, and hopefully by doing so, I don't have to aggressively introduce too many placeholders, which eventually will cause too much overhead for me. So that's kind of the idea behind the design of linear hashing. With that being said, let's try to understand this together. This actually is a little bit more difficult to understand than extendable hashing.
So the idea is as follows. You're going to use what we call a family of hash functions. A family of hash functions is just a set of, like you guys, a family of students. If I view you not as a student, I view you as a hash function. In fact, you can be a hash function, right? Because I can ask you, what do you think about Utah football? What do you think about Utah football? Each is a hash function giving a different value. The input is the same key, but giving a different value, right? So each is a different hash function. You may say Utah football is good, you may say Utah football is bad. I don't know. I don't know your opinion. Just you can guess. Right? So a family of hash functions, H0, H1, H2, all the way down. Right? So what is so special about these hash functions? What's so special about these hash functions?
Well, the ith
Hash function
HIK
satisfies the following condition: is using what we call a meta hash function H. So they all are constructed based on the same meta hash function H, super hash function H. Mod 2 to the power of I times 2. So what's so special about this? Someone make an observation of this hash function? So what's going on is H0 of x equal to what? Hx mod n, right? H1x equal to mod what? 2. Very good. See how this goes, right? Now, let me ask you this question again. What's so special about these guys? What's so special about these guys? Well, you are doubling the output range of this hash function. Right? You're essentially doubling you're simply doubling the output range of these hash functions, which is the same as doubling the output range is the same as looking at one more bit each time. Right? Doubling the output range is the same as looking at one more bit each time. So it's the same as what we were doing for external hashing. Essentially it's the same. Does that make sense? Okay? We're doubling the size of output range, and that's essentially the same as looking at one more bit each time. I mean, in fact, it's very simple to understand. If you any given number divided by 2, that actually tells you the last one bit. Divided by 4 tells you the last 2 bits. Divided by 8 tells you the last 3 bits. Divided by 16 tells you the last 4 bits. So on and so forth. That's essentially what we're doing. Okay? All right. Now, you can look at the pseudocode, but I think the pseudocode is not that useful in a classroom setting for you to understand. So I'm going to show you this picture here. And once you understand this, you can go back and review those pseudocode yourself, offline. So what's going on? What's going on is the following. Unear hashing. Alright. So you no longer have directory entries. Compared to extendable hashing, you have to maintain those directory entries, right? No, you no longer need to maintain them anymore. All you need to maintain is a set of buckets. Initially, how many buckets you have? How many buckets you have? Well, given that first hash function h0x is hx mod n, you know you have n buckets to begin with. Each of this is a bucket and a page. A bucket is just a page. Initially, each bucket contains a single page, where this page is going to hold data entries hashed into that bucket. Does that make sense? Initially, you use h0x to determine where they go. Which is hx mod. So the output value is always a value between 0 and minus 1. So far so good? So initially use this to determine where they go. So you basically have a string of x coming in and go to these different buckets. Of course, each is a data entry of some sort. Right? That's kind of the setup, okay? Initially, everything is fine. What is beautiful place? Seriously, when you think about Earth, when Earth had the first hundreds of people, they're not going to fight, right? Each of you can have a continent on your own, right? But eventually, you have a billion people on a continent, they start fighting, right? That's when you have overflow buckets. Yes.
What do we have to each bucket that data record?
Inside each bucket is just a set of data entries. We do not store records in data bucket. We store data entries in buckets. Does that make sense?
Data entries.
Data entries,
Yeah, entries.
not data records. Okay, that's why I'm drawing these guys. These are data entries, not records.
Each data entry, it's like a pointer to the data.
Kind of.
data
Each,
record.
I'm using alternative 2, which has a third key value k and a record ID. And you can think about that record ID as a pointer to the physical location of record on some data pages. Okay? So that's what we have. Initially, things are fine. It's a beautiful place. They each go to their own place, everything is fine. But eventually, you run out of resources you have. Right? That's essentially what happens. And you have overflow buckets. So what's going to happen is, I'm going to introduce what we call a next pointer. And initially point to the very first bucket. And suppose I have the ith bucket is completely filled up. And yet another guy is hashed to this bucket. What's going to happen now? You have to introduce an overflow page to accommodate a new data entry coming to the ith bucket. That makes sense? In extendable hashing, what happens? In extendable hashing, you would split this particular bucket and introduce a new bucket down below to redistribute these guys right away, so that you do not have overflow bucket at any given time, right? That's what happens in extendable hashing. But because of that, it introduces, potentially can introduce high overhead in terms of number of direct entries you have to return, right? So what happens now? In linear hashing, I do not do that. In linear hashing, think about the police station example. This is like somebody calling you, oh, I have a cat running around. Can you help me get a cat? Say, okay, noted, problem noted. I'm gonna come to you at some point, but not right away. What happened is, in linear hashing, instead of split this bucket, I'm gonna split the next bucket. Next bucket initially point to the first bucket. So I'm gonna move the next pointer to the next bucket and split this bucket. Suppose this bucket has, I don't know, just a few items, like 3 items. What I'm gonna do, I'm gonna color. What I'm gonna do is I'm gonna introduce a new bucket here, the nth bucket, and redistribute these entries. There are a few possible cases, right? There are a few possible scenarios. One is all of them stay here. The other possible scenario is all of them goes here. What's yet another possibility? Some stay here, some stay here. Let's say this is moved to here. The question is, how do you do this particular redistribution? Who decides who to stay where? Well, this redistribution is done by using, someone make a guess? You of course cannot use H0x to distinguish them, because if you use that, they will be the same. That's why they all end up in bracket 0, right? So which one you gonna use? Excellent. I'm gonna use H1x to redistribute these three guys into the existing bracket and this newly created bracket. Why H1x help? Because you're looking at, like I said, one more bit to distinguish them. That's the idea. That's it. That's linear hashing. You may wonder, wait a minute, I haven't dealt with this problem yet, right? Well, the point is, eventually, if this is a really rough city, eventually problem keep popping up everywhere. This next pointer will keep moving down. Eventually, it will come to here and split these guys, meaning cat being taken care of eventually. But if this is really a safe place, really quiet, no police incident report anyway, in that case, occasionally you have one or two overflows here and there, fine. Big deal. Huh? I don't care. That's the point of behind the design of this linear hashing. But by doing this, eventually what I got, eventually what will happen is, I will move the next pointer down here. By that point, hopefully this is gone. But I have redistributed this already. That makes sense? But I have, by this point, how many brackets I have down below? Can I take a guess? How many brackets in total I have? Huh? How many red brackets I have by that time? N-1. Sorry, n buckets, right? Sorry, n-1. I haven't split the very last bracket yet. Every time you move down the next pointer, you split an existing bucket of that pointed by the next pointer, you introduce a new bucket. By the time you move down here, how many times you have moved down already? You move down by n-1 steps, which means you have created n-1 new buckets. But if another overflow happens, let's say here, you're gonna split that n-1 bucket. By that time, you introduce yet another bucket down here. You have total of n buckets. At this point, what happens? In total, you have 2 n buckets. You should reset the next 2 here and throw away this altogether and start using H1x. The whole process recurs. And H1x is capable of indexing 2 n buckets. And this process continues. That's essentially the idea. Okay, behind this. Now, if you understand what I said so far, coming back to here, the red buckets are those from this particular slide. The red buckets are those who have been splitted already. And the green buckets are the buckets from the current level that are yet to be splitted. The blue buckets are the ones that were just newly created by the splitting of those red buckets. And you are guaranteed to have equal number of blue buckets and red buckets. By the end of the current round, you will have no green bucket left. You only have red bucket and blue bucket. You're going to have equal number of red bucket and blue bucket by that time. And you reset all of them to green buckets and move the next pointer back to the first bucket. And you increase the hash function to the next level hash function. That's the algorithm of linear hashing. Okay? Now, how do you do searching using linear hashing? How do you know where a particular value goes? How do you know where a particular value goes? Well, what you do is the following. You will always use the current level hash function h level to do the searching. You hash the search key value k, and look at which bucket it goes to. If it goes to a green bucket, you know the data entry must be there, or it does not exist at all. If it goes to one of the red bucket, what happens? You know it's either there or in the blue bucket. How do you know for sure? Well, if you know you are in a red bucket, you use h_level +1 hash function to hash the search key value again to figure out whether it is in a red bucket or blue bucket. All that being said, you may wonder, all sounds good, but how do I know I'm red, blue, or green? I'm colorblind.
Because you know where your pointer's at, right?
Yeah, you compare, once you use the h_level hash function to figure out which bucket you are at, you look at your bucket number and compare that against the next pointer value. You know you're blue, you know you're red or green. That's how you do the searching, okay? There are some examples. I'm going to skip this. Do you want me to run this or do you want me to skip this? Let me do a show of hand. How many of you want to go through this example? How many say skip? Okay, let's go through this. What about the rest? Don't care? Alright. Alright. Okay. So, this is my level 0 hash function, this is my level 1 hash function. Which means, what's my value of n in this case? What's the value of n in this case? It's 4, right? Because my level 0 is indexing 4 buckets, which means n must be 4. The value of n must be 4. Okay, so that's my initial setup. And I insert 43. This is not the search key value k. This is the hash value of that search key value. So the hash value of some search key value is 43, which translates to this binary number 101011. Using level 0 hash function, because I'm currently in level 0, where this guy should go? It should go to 11. This bucket, I introduce an overflow bucket. And because there's an overflow, what I do? I have to split the next bucket, not the overflow bucket. I have to split the next bucket, which is the first bucket. So I split that. I use level 1 hash function to index them, meaning all the ones with 0, 0, 0 will stay here. I look at the last 3 bits instead of the last 2 bits now. And all the ones with 1, 0, 0 will end up with in that new bucket. So this is that red bucket, this is that blue bucket, these are the green buckets. If I refer to this. Just continue. If I continue this for some number of steps, I reach here. I insert 50 at this point, which is where it should go. Where should 50 go? It should go to this particular bucket because the last 2 bits 1, 0. I'm still at current level 0, right? So I should be still using level 0 hash function to index this. So 50 goes here. But because that's an overflow, I split the next bucket. The next bucket currently points to the last bucket in the level. So I will split that using level 1 hash function, which is to say I look at the last 3 bits. If it's 0, 1, 1, they stay here. If it's 1, 1, 0, they go to, or 1, 1, 1, they go to the new bucket. 0, 1, 1 stay, 1, 1, 1 goes here. So these guys. And that overflow bucket 50 introduces the overflow, that overflow bucket stays. But because I have split the next bucket, I reach the end of the current round, I reset next to the beginning. At this point, these are my red buckets, these are my blue buckets. And I reset all of them to my green buckets. I continue to the next round. At this point, I can throw away level 0 hash function, start using level h1, level 1 hash function and level 2 hash function for split purposes, for splitting purposes. Okay, that's it. Searching, I talk about how to do searching, right? So for example, if you want to search for 44, what happens? 44 is 0, 0, so it goes there, you find it in the first bucket. But if it's like this, how do you find 44? Well, you use level 0 hash function. Find that it's 0, 0, right? It goes here. But now you know this is before the next pointer, so it's one of the blue, one of the red buckets. So you should use h1
to figure out whether it's in this red bracket or it's in this blue bracket. If you look at H1, the last 3 bits is 100. You know it should be in the blue bracket instead of the red bracket. You find it. Okay?
That's linear hashing. The deletion of it I skip. It's the reverse of it. I allow you guys to figure out the details yourself. Okay? The only thing left is how do you design a good hash function H? There are millions of different choices, right? One is, like what we said earlier, this mod n I'm gonna ignore because if you target is to map them to size n brackets, you're always gonna mod n, no matter what's the design here. So I'm gonna ignore that. Okay? There's always gonna be a mod n term for any hash function you come up with. If your goal is to map them to size n domain, right? So that n brackets. It is a good hash function. Or what about? It is a good hash function. I don't know, some really complicated curve. This is x, this is my y, this is the output. My output is y. Right? So then you look up, okay, given this x value is this one, given this x value is this one. This can be a really, really complicated curve. That make sense? This curve is simply a linear curve. Where this is b, and the tangent of this is a. That's ax plus b. No? Should go back to the geometry, right? Ax plus b is exactly this. Why? Because when x is 0, what's y? Y is b. So when x is 0, intersection with y is b. And the tangent of it, meaning this part, divided by this part should equal to angle of the curve, which is a. Okay, that's what it is. And what about hx equal to 1? What curve it corresponds to? Huh? What curve it corresponds to? Tell me what that curve corresponds to? No, it's just horizontal. In fact, hx1 equal to 1, you can think about that as so a is 0, b is 1. That's essential. And if you set h to 0, b equal to 1, you get this curve. So it's just a special case of that. Okay? That's the geometry view of the world. You know, every one you should have 2 views of the world nearby you. One is a mathematical view, the other is a geometry view. I always have that in my mind. And one way is to describe that in mathematical term, ax plus b. Or you think about this, oh, it's just a curve. Now, the question now becomes the question we are trying to answer is the following. Once you understand what I said so far, you realize this actually is not a trivial problem. What essentially you are trying to solve is given a bunch of x values, you want to distribute them into this space of y so that distribution is uniform, balanced, through some particular curve. So there are tons of millions, billions of different curves. Which curve is the best? Which curve is bad? Which curve is good? How do I answer that question? That's essentially the problem we're trying to solve. Do you follow me? Okay, how do we do this? To formalize what I said, let n square n. This is the mathematical notation. What that means is it denotes a domain of size n. This essentially means from 1 to n. Integer values, 1 to n. Or 0 to n minus 1. Let me be consistent with what I have on the slides. Denote the numbers 0 to n minus 1. And that any set S belongs to a universe such that the size of S is small n. The universe U
universe U can be anything. Okay? As long as the element of that universe is from this domain 1 to n, 0 to n is 1. Okay? So U is kind of like every possible set that consists of elements from this domain from 0 to n minus 1. Okay? That's what the universe U stands for. Okay? All possible value sets. And S is just one particular set of that, subset of that. And we want to support the following operations, which is add an element to S, delete an element from S, and query whether an element exists in S or not. Where X must be a valid element. A valid element, meaning that it must be a value from 0 to n minus 1. Okay. First, we consider the static case, which is a fixed set S. Now, note that even though S is fixed, we don't know S ahead of time. This is critical, right? We only know S is fixed, but you don't know the values in S. You only know somebody choose a set S for you, it's fixed, but you don't know all the values in S. But you do know once that person made that choice, he or she cannot change the values in S. Even in this case, how many possible choices do you have? Well, your domain size is n, capital N. How many possible such sets as you have? It's n choose n, right? It's n choose n, right? Capital N choose small n. Why? Because the size of S is small n. You have a total of n capital N choices you can make. Whenever S is set, which means it's duplicate free, right? It has no duplicates. Set has no duplicates. I'm not talking about Marquez set, I'm just saying set. Set has no duplicates. So you have n choices, capital N choices, and you have n small n choices to make. How many possible choices you have? N choose n, capital N choose small n. That's the simple. Okay? Okay, if you have 3 elements, 1, 2, 3, and you make a size 2 set out of it, how many choices you have? 3 choose 2, which is equal to 3 choose 1, which is 3. Why? You're going to have 1, 2, 1, 3, and that's it. You have no other possible choices. Of course, with the growth of capital N and small n, this value becomes fairly big. Okay? So you still have tons of choices to make. Capital N choose small n number of choices. So the static case is given a set of S, given this set S of items, we want to store them so that we do lookup quickly. In other words, I want to know whether somebody belongs to this set or not. You need to answer that question really quickly for me. A naive solution is what? Is to pay order n cost. If I want to know somebody exists in a set or not, I just do a linear scan of the set. Right? But this will be ridiculous, right? Imagine if this set S is, every element means if this person has visited google.com today or not. Okay? If this person has visited google.com today or not. And what's that capital N? About 6 billion or 7 billion, right? The world population. Because for each person, you may have a value of he or she has visited or not. So capital N is 6 billion or 7 billion, something like that. A small set S N is, I look at, I choose the subset of world population, I remember whether they visited Google or not. And I just want you to answer this very simple question, is Feifei in that small set S or not? To answer that, naive solution is what? To linear scan the small set S every time. If you do this once, okay. But if everybody asks Google this question and Google linear scan this, in the worst case, if Google has to scan billions of records every single time, that's ridiculous. Right? That's essentially the problem we're trying to solve. Can we do better? So that's the static case. The dynamic case is here we have a sequence of insert, lookup, and perhaps deletion requests, meaning add, query, and delete. And we want to do all of this efficiently. So those are the two different setups. Okay, two different setups for this problem.
So hash function basics. So we're going to solve this problem by designing good hash functions. But in order to understand the design of those hash functions, we need to understand the basics.
We will perform insert and lookup by having an array A of some size M, capital M.
And a hash function H. And this hash function H satisfies the following. It's a mapping from the universe U, in other words, from the domain N to zero to M minus 1. And I have an array A of size M. That means I have A0, A1, A to M minus 1. I'm basically trying to decide for any small element x from my universe U where this x should go. Here, or to here, or to here. And I want to make a balanced distribution of arbitrary elements from the universe to this array A, so that not a single element from this array is overburdened. Does that make sense? That's kind of the problem we're trying to do now. If this n, which equal to the size of the universe, is small, this problem is fairly trivial, actually. But unfortunately, n typically is very big. And collision may happen, right? Which is collision refers to the fact that hx, hy, and collision is our enemy if you think about it. Why? Because collision means if you have too many collisions, that means you do not have a balanced distribution of these elements into this array A. Do you follow me? So you want to, basically the idea is you want to reduce the probability for clear. You want to reduce the probability for clear. The question is how to do that. The following discussion will be fairly involved, so I will stop right here. We start on Tuesday. That Tuesday lecture is really, really important. I encourage all of you to physically come because the discussion is fairly involved. It involves some in-depth discussion on some theoretical foundation for designing a good hash. It's not trivial to understand, so I encourage all of you to come to the Tuesday lecture. That being said, I will release lab 2 today after 5 p.m. as well as homework 2. I don't think we do release it today. So we're still missing submission from team 12, team 19, team 26. Team 10 made a submission during the lecture.
Yeah, I would like to learn for the state.